23,173 has each pair of its digits in order of prime number, because we've got 23, then 31, then 17, and 73. And all of them are different. We're asked what is the largest integer that meets these conditions. So basically, we want to try and put together as many two-digit primes as we can, but forming the largest number. So you might be able to write down your two-digit primes. My advice would be take it steady though, make sure you don't miss any. And a really good approach for this is to use something called Eratosthenes' sieve, which sieves out all your prime numbers. So 1 is not a prime number by definition, then 2 is. I can now remove every other multiple of 2 from this grid. And hopefully you see what I mean now by sieving them out. It's take a little bit of time, but I recommend, getting a grid and doing it along with me. So this makes 2 the only even prime. Next up then, 3. 3 must be prime, because it's not divisible by 2. I can now get rid of every multiple of 3. Now I've already got rid of the even ones, so I can just keep adding 6 onto 3, and then on so on, to ensure I get the odd multiples of 3. So 9, 15, 21, and so on. You have to be careful, because otherwise if you miss any, then you might end up thinking it's prime when it's not. All right, brilliant. Multiples of 5, we've got rid of most of them, but it's going to be the remaining ones that end in 5. And then 7. So I'm just going to count up in 7s now to make sure I've got them all. So 21 I've got, 35, 42, but 49 I haven't got because that one is 7 times 7, so I wouldn't have ruled that one out yet. 56, 63, 70, 77. See, that is 7 times 11, so I wouldn't have ruled that one out yet. And then 84, 91. That's actually 7 times 13. The next one is 11. But we've actually already crossed out all the multiples of 11. In fact, at this point, we've got them all. All the rest that are not crossed out are necessarily prime. The reason for that is that the square root, to test whether a number is prime, you only have to test its prime factors up to its square root. So let's say I want to test whether, I know this is not on the list, but let me go with 97, one that's on the list. So root 97 is about root 100 or 10. It's going to be less than 10. So I only need to test 2, 3, 5, and 7 to see if root 97 is prime. Because if none of these go into it, then we're not going to have a prime that's above the square root that's also going to go into it, because it would have to then multiply by a prime below the square root. So it's enough just to check the primes up to the square root. I only have to check 4 numbers. I don't have to check things like whether 6 goes into it, because if I know that 2 and 3 don't go into it, or even just 2 doesn't go into it, then 6 definitely isn't going to go into it either. So because I've actually tested all the primes up to, well, in fact, 11 here, every single other number is going to be prime. It's a great method for carefully obtaining these primes. Now, I'm going to distinguish between 2 types of prime, because if I have a prime such as 23, then I cannot put it anywhere in my number except at the start. Because if I put it later on, then I'm going to have a prime that ends in a 2. And the same goes for any prime that starts with a 2, a 4, a 6, or an 8, because these are all even, or in fact a 5. because if it starts with a 5, there's no two-digit prime that ends in a 5. And I should have said, actually, at this point, I'm going to cross out the one-digit primes. Yes, I know we can get some that end in 2, 3, 5, and 7 here, but they're not allowed to be my number. So let's highlight the primes that I can put somewhere in my number and the ones that have to go at the start. So for example, 11 can actually go anywhere. There's no, because I can have another prime that ends in a 1 or one that starts with a 1. Same with 13, 17, and 19. But these ones have to go at the start if we're going to put them in. 31 and 37 can go anywhere, but these cannot. Oh, and 53 and 59 for similar reasons. 61 and 67. These can, in theory, go anywhere. So I've classified my primes into two different types. So that's sorry, that's meant to be blue because I'm writing on a yellow screen, it's not showing up. So let me just write in pen. It's the highlighted blue primes. So the aim, therefore, is to use all the green primes and the largest possible blue prime at the start. This number will necessarily be bigger than any number that doesn't include all the green primes and doesn't include, say, a blue prime at the start. So that is the best that we can do. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 green primes, and then one blue prime. So the best we can do is use 11 primes. Now let me write down the green primes and put them in a list. So I need to start thinking how I can link them all together. And of course, at this point, you could just try some lists out, but we have to show that whatever we get is necessarily the largest number. So I'm just going to be a little bit more careful. And I'm going to look at what they end in. So we've got 1, 2 that end in a 1. And while I'm at it, I can see that 4 start with a 1. Wait, that's not quite right. 11, let me just underline them. 11, 31, and 71. So sorry, 3 end in a 1. And 4 start with a 1. Because remember, we have to link them up, so this is worth doing. We've got 1, 2 end in a 3, and 2 start with a 3. We've got 1, 2, 3 end in a 7, and 3 start with a 7. We've got 2 that end in a 9, and 1 that starts with a 9. Now, this has some consequences actually, because whilst this seems okay, the fact that only 1 starts with a 9 means that because 2 end in a 9, I'm going to have my overall number must end in a 9 for me to, that is for me to be able to use all 10 of these and then one more. And because 3 end in a 1, but 4 start with a 1, then my first green prime, okay, I know we got these blue ones as well, my first green prime must start with a 1. Let me just talk a little bit more about that before I move on. So I've got 17, 71, and 97. But you can see there's an issue here because there's no other one that I could connect to 97 if I connect the 17 and the 71, or vice versa if I connect the 17 and the 97. So it must be that I end in a 7 so that I don't lose my connection. And the same goes with 1, because if I've got my 11, my 13, my 17. Oh, sorry, there's kind of lots that have 1 in. Um, but I could maybe connect this. I could do 1 1 1 3 3 1 1 7 7 1. But you can see I'm then out of them. I don't have any more. So I have to. Sorry, have I missed any? Oh, sorry, then 19. So that would be okay, but there's nothing to connect to this 1. So that has to go on the left if I want to then connect a blue prime to it to make it bigger. So, right, we're going to try to start with the largest one that starts with a 1 then. And then let's just give it a go. So if I go with 19, then my next one has to be 97. Remember, I'm trying to make the number as big as possible, so I'm going to be bearing that in mind. If I now, I don't want to use 79 because I want it to end in a 9. So I'm going to ignore that, and actually that would mean that 79 goes at the very end. I'll just put that in a bracket, which means I can then use the next biggest one, 73. And I could try and use the next biggest one, 37, to see if it works. Then I'll have to use 71, because remember I have to use 79 at the end. Right, now I can't use 17 at this point. 17 is going to have to go next to 79, so I'll use the next biggest one, which is 13. And then I can use 31. And then this is where I'll bring in 11. I could have put 11 after 71, but it makes sense to move it further down, far down as possible, because it's smaller than 13. So now I can use 17, connect to my 79, and that will be the last one. And this is a way of writing down all 10 primes then to make a number where our adjacent digits are prime. And I've used this little, like the key bit was using the fact that it had to end in a 9 and it had to start with a 1, and then I just went for it and tried to make the number as big as possible. So the only thing now to say is how can we make this number bigger? Remember, we might have wanted to use 89 at the start, but it just wouldn't have worked because it ended in a 9 and we didn't have any that worked. So I need to find the biggest blue prime that ends in a 1, and that's going to be 61. So whilst I haven't written all my explanation down, I've been doing it verbally, and this number here is the largest number that satisfies the condition. Wow. Let me finally just summarize this solution. So we're trying to find the largest number where pairs of neighboring digits are primes, and they've all got to be different. So we first of all wrote down all of our 2-digit primes. We just noticed that any that start with an even number or 5 must go at the start because there's no way they could be elsewhere in the number. So I highlighted them in blue. The green ones could go in different places. We had 10 green ones. So the best we can do is use all of these and one of the blue ones at the start. Any number with fewer primes would be smaller, and there's no way that we could use 12 primes. So we wrote down the list. I just identified that 3 end in a 1 and 4 start with a 1. That means that the second prime number, the one that's not the blue prime, has to start with a 1. And 2 end in a 9, 1 starts with a 9, which meant that the ending prime has to be a 9. With that in mind, I just started it off with the largest possible prime that starts with a 1, because that's going to be give a larger number than if I started with, say, 11 or 13 here. And then I just carefully maneuvered through, explaining each step and justifying why we should use the next, like the largest prime that would be possible, or we're not allowed to use it because it would cause problems. We had to bring in a 79 at the end, for example. Justified that, and that gave this number here. There's no way that we could get a bigger number because any other number, like, either would be smaller, well, basically, yeah, any other number would be smaller because you have to use a 1 here, you have to use a 9 here, and I've explained as we've gone along why, like, we've maximized the primes to the right. So yeah, really good. I hope you enjoyed that question. It's fantastic.